All right, last task for choosing between linear and exponential functions. Here we have a sea turtle population is studied in a coastal area. The data show sea turtle population estimates during a 5-year period. Find a model for the data and analyze its fit using a residual plot. That's something new. We haven't plotted our residuals yet, but it's pretty straightforward. So I'm going to show you how to do that and how we know from the plot whether it's a good fit or not. So first we need to find a model for the data. If we notice our common, here they give us, here's the year from 0 to 5, and here's the estimated population. If you notice our common difference, it is not common. This difference, it goes down by 1600, then down by 2000, then down by 13, so it went the other way around. So definitely not a common difference. So I can tell there, they're not even close. So this has definitely not a common difference. Okay, so I can tell there that it's definitely not linear. Okay, but if I look at the common ratios, they're not the same either. The common ratio is not the same, and this is way more common with real life data. Real life data very rarely fits an exact linear or exact exponential, but the exponential is a better fit than the linear. These numbers are all over the place, down by 1600, and that goes down by 2000, a whole lot more than down by 1360. Whereas if we look at the common ratio, they're not all the same, but they're all pretty close, 0.92, 0.89, 0.91. They're all around that 0.9 area. So I think an exponential model is going to be the best fit. It's not going to be perfect. Unlike these ones that we did earlier where the equation hit every single point, this one isn't going to hit every single point, but it's going to be pretty close. That's why we're going to go ahead and analyze those residuals. An exponential model is going to be the best fit. So my exponential model, a times b to the x. I can tell here my a is 1900. That's where we're starting. Sorry, 19,000. Now for my b. I could just pick some point in between here. I think the most accurate is going to be to average them. So for the B, let's go ahead and use average isn't always the most accurate, but let's go ahead and let's average these ratios, and we'll use that average, and then we'll use that to look at our residuals. 0.92. So to average, we add them all up. 0.92 plus 0.89 plus 0.91 plus 0.94 plus 0.95 equals. Now divide it by, there's 1, 2, 3, 4, 5 of them, divide by 5. So 0.922. Okay, let's go ahead and let's try 0.922. Okay, 0.922. So this is a decay function, which makes sense because the population of turtles is decreasing. So it is a decay function. So an exponential model and a decay exponential model. Okay, so there's our equation, 0.922. So now we're going to go ahead and look at the residuals. So the residual is I would need to plug in each of these and take the difference. I could do it all by hand. I'm going to use Excel. And to prevent me from jumping back and forth between devices, I'm going to try to use Excel on my iPad. We'll see how it works. All right, so I already have the data in here. So there's my data right there. Okay, so there's the year and the population. So now we need predicted. So now I need to use my equation. So equals, and what did we use? 19,000 times, so times, and it was 0.922 to the, and then we're going to use that first box right there. So there's my predicted. Now, normally on your computer, you would click that little box and go down. On the iPad, you have to hit fill first and then drag down. Okay, so there are my predicted values. Now to find the residual, I need to take the actual, so equals, minus the predicted. So the first residual is 0. Again, let's fill and let's drag down. All right, so there are my residuals. Okay. So if you notice, all of my data sets are too big based on this model. They are all too big by quite a bit. We're going to go ahead and look at the graph of these residuals. Okay, so let's go ahead. Will it let me? Can I do screen by screen? I can. All right, so to graph these residuals, what the plot of a residual looks like. So here we're going to do our plot of our residual, and our data points are only the numbers, the years 0 through 5. So I only need the positive axis. So, but I want both positive and negative. So this here is still going to be time, and this is going to be a residual plot. So at time 0, what's the residual? The residual is 0. Okay, so that's a nice one to plot. We'd have 0, 0. At time 1, let's count by 2's here. So 1, 2, 3, just to spread it out a little bit for 5. What, we only have those 5 years. Okay, but here I'm going to have to go to all the way up to 118. So let's count by, and then what, 800 is my biggest right there with that 800. So I need to go to 800. So let's have each of these be 100, 200, forth and so on. So at 1, I'm negative 118. So that would put me right about here. Let's do the residuals in red. So negative 118 would be here. For 2, it's negative 1, 2, 3, 4, 5, 6, 7, 50. So right about here. For 3 is negative 851, 7, 851. For 4 is negative 530, 1, 2, 3, 4, 5, 30, right about there. And then for 5, negative 139, negative 1, right there. Okay, so there, I plotted my residuals. Now you might be like, okay, I graphed those. How does that tell me if this is a good fit or not? I can tell by these residuals it's not a good fit. For it to be a good fit, it's not a good fit because they are not evenly spaced over the x-axis. Okay, I'm going to show you a quick graph of what a good residual for a good fit would look like. If the residual is a good fit, they would be evenly spaced over the x-axis, meaning like one up here, one down here, up, down, up, and there'd be the same number both above and below. So this is an example of a good fit. Because you don't want all of your points, like if we look back at that, all of my points were too big. They were all too big. So it's not a good fit. Some of them should be too small, like you should be kind of evenly spaced on either side. So not all of our residuals were negative except for one. They should be both positive and negative and the same amount positive and negative. So that is an example of a good fit, is this one down here. Is example of a good fit. This one, not a good fit. They're all back here. It's bottom heavy, meaning all of my predicted values, the actual values were all smaller than my predicted values. So it's not a good fit. So since we came up with one, so the averaging was not a good fit, what's another method we could find? How can we find one that's a better fit? How can we find a better fit? Our calculator. We can now use our calculator to come up with an equation that's a better fit for these. So we bring up our calculator. We would need to go to Stat and Edit. And we have the point 0 to 5, so we will not need these bottom two. So I can, let's see, delete that one and delete that one. And we'll delete these bottom two here. Okay, so at 0, we have 19,000. 1, 2, 3. 17,400. 15,400. 14,040. 13,200. 12,500. Excuse me. All right, so there's our data set. Now that we have it in there, we can go Stat, over to Calculate, and we want to come down and do an exponential regression. List 1, list 2. I'm going to store this. Oh, I'm sorry. Calculate. Exponential regression. Did it again. Sorry. This doesn't work the same. Okay, that's not going to work. All right, we aren't going to store it. I would go here and there we are. Vars over to y vars, function, y1. We're going to go ahead and put it in y1. And there's our equation. So if you look there, it actually changed my a. So a better fit, so let's call this g of x. We'll give it a better fit. Or actually p of t is what they tell you to use. If we look over here, they say p of t equals. So my a is 18712 times my b is 0.917, I don't know, let's go to 5 to the x. Okay, so there they say that's a better fit. And so if we go, my plots are on, there's the equation, I go to graph. Again, I can't see it because window issues. So this one for my window, I need to see from about 19,000 to 12,500. So my minimum is about 10. We'll go 10,000, 10, 1, 2, 3, up to 20, 20, 1, 2, 3. Okay, so there's my line, there's my points. So that might be a much better fit. Let's go ahead and let's go to Excel and let's compare those residuals. Okay, using this one instead. Again, I'm going to plug in kind of the rounded. So my population predicted here, instead of using that equation, let's clear that one out. And instead, let's get rid of the keyboard. Sorry. We are going to use this one, equals 18,712 times, and then what do we have? 0.9175 to the this. Yep. Okay, then now I need to again fill it down. So it applies to all of them. But what's nice is now it's adjusted my residuals as well. Now look at my residuals. If I was to do a residual plot of this, and we can go ahead and let's do a residual plot real quick. If I was to do a residual plot of this, and we're not going to do, it's not going to be super perfect. We're just going to go ahead and plot one in. So a residual plot of this one, if here's 1, 2, 3, 4, 5, there's 5. Let's see, at 0, it's 288. So let's go by 100s here. There's 100, 200, so forth, 300. So 1, it's 288. So it's like almost here. Oh, sorry, at 0, we'd be there. At 1, we'd be 231. At 2, negative 1 to 300 and something. 3, negative 400 and something. 4, negative 60. So I don't know, right about here. And 5, 333. Look at there. How many? We have 3 plots above, 3 plots below, and they're close-ish to the same distance above and below. Much better residual plot, much better fit. And even looking at our calculator, we can look at that R value. That R value is 0.98, 0.99 is the R, and the R to the second is 0.98. Again, the better, closer to 1 or negative 1 that is, the better the fit. Okay.